This is Physical Chemistry, Part 1, Thermodynamics, Chapter 9, Ideal and Real Solutions, Section 9.1, Defining the Ideal Solution. In an ideal solution of A and B, the AB interaction is the same as the interaction between A and A. It's also the same as the interaction between B and B. This is to ensure, after we mix A and B, there's no change in the attraction or repulsion between a molecule and its surrounding molecules. For example, when we mix benzene and toluene, after the mixing, each benzene is surrounded by other benzene molecules and some toluene molecules. However, its environment is very similar to that in pure benzene, and same for toluene. So this is the so-called ideal solution. Raoult's law. In an ideal solution, we can easily calculate the vapor pressure of each component. For example, the vapor pressure of component I in a solution is the mole fraction of that component I multiplied by the vapor pressure of pure I. That's it. For example, if we mix 1 mole water and 1 mole ethanol together, assuming it's a nearly ideal solution at the room temperature, we know pure water has a vapor pressure of roughly 0.032 bars at the room temperature. Now the mole fraction of water is only 50%. It's not 100%. We simply just need to multiply this 0.032 bars by its mole fraction, 50%. So it's 1/2 of 0.032 bars for water. Why is this vapor pressure of component I in a solution proportional to its mole fraction? It's very simple. The vapor pressure of a component in a solution is proportional to the evaporation speed of that component. And now if we compare these two flasks, over here we have pure water, over here let's say we have 50% of the water. Then we compare this surface and this surface. On this surface, only 50% of the molecules are water molecules. That will reduce the evaporation speed of water by 50%. Now let's look at the condensation speed. So in this flask and this flask, supposedly when both flasks are at equilibrium, the condensation speed of this one should be equal to the evaporation speed. Same here. Now the evaporation speed of this one is only 50% of this one. That means the condensation speed of this one is only 50% of this one. How can that happen? Well, very simple. The vapor pressure of water in this flask is also 50% of that one. And then in this flask, the condensation speed and the evaporation speed are both only 50% of this one. You don't really have to have two similar components to make a component in the solution to obey the Raoult's law. In a highly diluted solution, the solvent always obeys Raoult's law. Why? Imagine you have 99.99% of water and 0.01% ethanol. Then each water molecule is anyway surrounded by other water molecules, just like in pure water. Therefore, the solvent in a highly diluted solution obeys Raoult's law. We cannot say that for the solute, because if you look at this 99.99% water plus 0.01% ethanol, in this solution, each ethanol is surrounded also by water molecules. So this environment is different than that in pure ethanol.